All right, let's go ahead and get started. So very close to done with the covering the stuff that's going to be on the test. I wanted to make sure that we had time to go over a couple of examples of finding arc length for parametric curves. So at the very tail end of class on Friday, we derived this. We basically very how we find arc length for Cartesian or curves defining y and x. But basically integral of this square root here. So the square root of dy dt squared plus dx dt squared over whatever interval is appropriate. So this is the setup, and I think we started talking about kind of how to set this up for the arc length along a unit circle. So I wanted to start with this one because this one we don't need an interval to find this length, so we can verify it pretty easily. So if we talk about this arc length here along or basically a one full rotation around the unit circle, what is that length? Yeah, so the circumference is the length. And with this particular circle, what is that circumference? 2 pi, right? So whatever integral we set up, we should get 2 pi as a result. So I gave you the bounds here. So from 0 to 2 pi for our interval of t. So what is the function we're going to integrate? How do we set that up? Right, so let's find those. So what is dx dt? Negative sine of t. And dy dt is equal to cosine t. So negative sine t squared plus cosine t squared dt. So that's the setup of this integral. Any questions on how we got there? All right, how do we continue? Right. So yes, that is going to simplify things a lot. This becomes the integral from 0 to 2 pi of radical 1 dt, or the integral from 0 to 2 pi of just dt. What is that integral? Simply t. So the integral, so basically evaluating t from 0 to 2 pi gives me 2 pi minus 0, which is exactly what you knew it should give you. How are we doing? Go ahead. That's the Pythagorean identity. So let me draw this unit circle a little bigger. Okay, so basically, how do we build out this unit circle and all the values on it? One thing so here's the motivation. Every xy value, like every set of coordinates for any points along the circumference of the unit circle, if we relate that back to the angle that projects that point, what does xy equal to? Xy is equal to the cosine of that angle. So the x coordinate is the cosine of that angle, the y coordinate is the sine of that angle. What if I wanted to find this length of this hypotenuse right here? I could set that up using Pythagorean theorem. X squared plus y squared equals r squared. And if I wanted to redefine it in terms of the angle, this becomes cosine squared theta plus sine squared theta. This is the unit circle. So what is the what's the radius? Radius is 1 squared or simply 1. So that cosine squared theta plus sine squared theta equals 1. That's true for any value thing. So that's where that comes from. What else? All right, let's do one more. So we've talked about this cycloid thing a few times and done a few different things with it, but so I think we've again, it looks like this. So basically it's this series of arches. And I think previously we have found, you know, some slopes of tangents in certain places. We found the area under one of these arches. Now I want to find out how long one of these arches is. So how do we set up the integral that's going to help us find one of those lengths? We need the bounds. So we could find those, or we could, let's talk about how to find it. And then we'll kind of fast forward to what the bounds actually are. So let's pretend we have not done it before. I want to find the bound. So I'd like to know where one of these arches starts. So what's a theta value for the start of one of these arches and the theta value for the end of one of these arches? I don't think it's x equals 0, but you're on the right track. It should be y equals 0. I want to know, so basically, I want to know the x values for which it returns to the x-axis. So that's where y equals 0. So if I set y to 0, r times 1 minus cosine theta equals 0. That is the equation that'll get us the bounds. I believe we found out previously that this happens every even multiple of pi. So it's going to touch the y, it's going to touch the x-axis an infinite number of times. Does that help us figure out what the bounds are? Zero to 2 pi. It really does not matter. Like, for example, could I have chosen like 20 pi and 22 pi? We're not going to do that, but why does that make sense? It's still going to give you a single arch. All these arches look identical to each other, but let's do the most sensible logical thing. So I think that's a good set of bounds. How do we set up the rest of this? So yeah, we need dx d theta, but yes. Dx d theta is what? You okay with that? Sounds good. We don't really need to because it's a constant. So let me give you a parallel example here. So what if I said that y is equal to 10x? What is dy dx? 10, right? Isn't that the same as me doing this? Dy dx is equal to 10 times basically the derivative of x. So you may not always think of it that way, but if you have a constant that's multiplied by the thing you're taking derivative of, you can sort of leave the constant aside and just carry it with you. So we can do the same thing with r here. So the derivative of y with respect to theta is r times what? That should be sine theta. Okay, so yeah, we need those pieces. What do we do with them? Okay, so square root of r squared sine squared theta plus r squared 1 minus cosine theta squared. Hopefully some convenient things happen for us. Yeah. Something else I'm going to do in the meantime is factor out this r squared thing. So the square root of r squared times sine squared theta plus 1 minus 2 cosine theta plus cosine squared theta. Any questions about where we ended up on that step? Basically I'm foiling out. So you sure? Okay. So yeah, when you square a binomial, it's first term squared plus the second term squared plus 2 times that middle term. No, I mean that we're not immune to that. To wanting to just square both things and call it done. So if I move on, square root of r squared becomes r. It's a constant, so I would like to take it outside the integral. Does anything inside this, the radical help us? I get basically square root of 1 plus 1 minus 2 cosine theta d theta. So r times the radical or integral from 0 to 2 pi of the integral of 2 minus 2 cosine theta d theta. How are we doing so far? Would we be offended if I called this sufficient? So I believe in your ability to go to Symbolab or Wolfram or something and get what that value is. But like many of the things we're doing here, and kind of looking forward to go into Calc 3, there's gonna be a lot of things you can do in Calc 3 where setting up the integral is what you'll be asked to do, because that is where all the challenge, where all the intellectual work has to be done.
This one was we can't really solve that easily.
Probably could do by hand. It'd take us more time than I care to spend right now. But yeah, Symbolab could spit out the number and show you all the steps, all that stuff. How we doing? So yeah, the last thing I wanted to show you was a couple examples on how to work with arc length in this coordinate system, like in this representation system. Other than that, I think we're screwed. How are we feeling about this? Okay, so I asked you to come ready with questions on what you'd like to talk about.